we have essentially is how to look at the derivative as its own function. So if I tell you that f of x is equal to x cubed plus 2x squared minus x, and I'm going to call it f dashed x now. You know, we were calling it f dashed a last time, but let's just call it what it is, because the variable is just cosmetic. Using the power rule, the shortcut, the power rule, we should be able to tell what the derivative of this is, right? So anybody want to have a shot at it? What would the derivative of this function be?
3x squared plus 4x minus 1.
You nailed it. You all comfortable with that? Right. So this section has really got two parts to it. One of the parts is you just basically do this, right? You find the derivatives. But we're going to focus on the early part. And the early part is how to sketch the derivative function y equals f dashed of x when you are only given a graph of f of x. Now, if I tell you this guy, you can find its derivative. And now, if I asked you to give me a graph to sketch it, wouldn't you just probably put it in the Desmos and copy what you saw, right? So it's quite easy if someone tells you what the function is, for you to find the derivative of that function and then graph this. Would you agree that'd be a quadratic? You could almost imagine what it would look like, right? And that's fine. But it's not so obvious how you would do it if all I give you is a sketch. So I'm going to take you through the types of situations where that's going to happen, and there's quite a few of them. So before I do that, let's take a standard polynomial function. Isn't that what polynomial functions look like, right? They go up and they go down a couple of times. And we are going to do a sketch of that function. And then what the homework does is they give you 4 pictures and you pick the right one. So that's how you kind of do your answer. And the way to approach this depends on the shape that you're given. If you're given a nice curve, like a polynomial, the first thing you do is you go looking for tangent lines. Would you agree that the top of that hill, the tangent line is horizontal? And would you agree at the bottom of this valley, isn't the tangent line horizontal? So far, so good. What number is the derivative when you have a horizontal tangent line? In other words, what's the slope of that line?
0.
Red, 0. So what you're going to do, and it gets a bit messy, but I'll try my best, is that you take those hills and valleys and you do an invisible dotted line. I know you can see it, but can you pretend it's invisible? And you drop it down and you put a dot there, because won't the curve pass through the x-axis at that position, right? Because its derivative will be 0. Would you agree that point has a 0 value, right? 0 height. And then you take the second one and you do that. And you put a dot here. And so we've basically broken this f of x into 3 regions. Now, let's look at region 1. If you take any point on this curve and you found its tangent line, would you agree its tangent line would be pointing upwards like this pen? Agreed? Tangent lines, or any line that points uphill, are positive, aren't they? Positive numbers. So I know that in this region, region 1, the derivative is a positive number. Now, in region 2, would you agree that any tangent line would be a line pointing down like my pen? Right? Tangent line. So if I pick this point here, wouldn't the tangent line be pointing down the way? And lines that point down the way, don't they have negative derivatives? So I shade here to say that the derivative curve is somewhere in this green shaded region, right? It's somewhere in this green, it's somewhere in this. What would the region 3 be? Positive, in which case I shade the top of the x-axis, or would it be negative in region 3? What would you do? If you pick any point in that curve, what would the tangent line be? Positive or negative?
Positive.
Right, positive. Now, once you've done all of that, so I want you to pretend that those dotted lines aren't there and neither of those shading, because won't the shape of this curve be basically a big happy face? So that's what the derivative looks like. Now, aren't there going to be some variations? Some people's happy faces are going to be skinnier and taller. Other people's happy faces are going to be wider, but won't they all be happy faces? That's the shape. Concave up if you needed it. So that's how you deal with polynomials, right? Nice, smooth curves. Any questions so far? Are you happy with this shape? Why this would be the derivative? The derivative is that red curve. All the other stuff was just to help me draw it. That's cool. Let's do still a basic curve, but with something extra going on. So this time I'm going to have a curve that looks like this. Right, so flat lines here, right? Goes up, goes down, and that flat lines here, right? And that's my original curve. And we're going to try and create what its derivative would look like based only on the shape of that thing. So first thing I'm going to do is I'm going to say, okay, there's a hill there, and there's a valley there. And that's going to be my way of separating the region up. And at this point, the slope is horizontal, so it's 0. At this point in the curve, the tangent line is also horizontal, so it's 0. And this is going to be my region 1, region 2, region 3. Okay, so not that much different from the one we just did. If you take any point on this curve and you find a tangent line to it, would you agree that it's sloping upwards and it's positive? What's it going to be in region 2? Positive slopes or negative slopes in region 2?
Negative.
And in region 3, would you agree it's back to being positive? It looks like a carbon copy of that question, but there is a difference. In this first question, aren't the slopes just continuing to go up and downwards forever? So won't the slopes get bigger and bigger? And that's why the curve's doing this. Do you notice at the end that the curve is flatlining? Great. Now, what's the slope of a tangent that's almost flat? Don't the slopes get closer and closer to being 0? So I'm still going to start with a happy face because there's no way of avoiding this region to that region and back. But now I'm going to curve round and flatline. And you might say, what's that all about? Would you agree that this curve is becoming horizontal and therefore its tangent has to be 0? You can decide how high this hill is or whether it's a little bit further to the left or right. It doesn't matter, there's variation there. But isn't that the basic shape of what that derivative looks like? Are we comfortable with that one? Any questions? Next one, totally different kind of shape. We are going to do a shape that goes along the way. Let's go to there, goes up the way, goes down the way, goes along the way, goes up the way. So how do you find derivatives of shapes that are made out of straight lines? Right, new puzzle. Now, when we did these shapes, didn't we start with horizontal tangent lines, and that allowed us to separate the shape? And that's good. That's what you do when it's nice curves, right? When it's hills and valleys, this is how you do it. In this shape, different approach. What you identify are the corners, because at the corners, something is changing. For instance, at that corner, isn't the curve going from being a straight line to being a flat line? At this corner, isn't it going from a flat line to being a line that's pointing downwards, and so on? So these are the key places. They're actually called critical numbers, if you want to know their number. And these shapes have a really weird thing that you will get used to once you've done enough of them. But right now, I have 1 region, 2 regions, 3 regions, 4 regions, and finally 5 regions, right? So far, so good. So you use the corners because they're critical places. That's where something is happening, something is changing. Now, if you choose any point on that straight line, would you agree that its tangent line is that green line? Right? And that means it's a fixed number. But is it a positive number or a negative number? What kind of slope do you have here?
Positive.
Positive. So you pick a number and you do that. Positive, right? Don't know why I've changed the green, but I have. Region 2. If you pick any point in region 2 and you draw its tangent line, don't you get a horizontal line? And does it not make it 0? Region 3, positive, 0, or negative. It's the same number all the time, but positive, 0, or negative.
Negative?
Yes. Region 4, positive, 0, or negative slope.
0?
0. And last but not least, in region 5, positive, 0, or negative. What do you get?
Positive.
Positive, right. Now, have you noticed that this graph is broken? It's not a continuous graph. At this point here, isn't the answer up there and then it jumps straight to there? And there's a good reason for that. At these corners, there really isn't a tangent line. Would you agree at that corner, is the tangent line 0? Is the tangent line 2? Is it kind of halfway between the two? There isn't a tangent line there. And we indicate you can't use me. Remember those open circles? That's what that shape looks like. When you draw an open circle on a graph, doesn't that mean there is no answer at that point? Right? There is no slope of a tangent line at a corner, right? Now let's be silly about it. Suppose I had a corner that looked like that, right? That could happen. What's the slope of the tangent line? Well, it doesn't really make sense. Could you agree that there's like almost anything could be a tangent line? Okay, coming up one side and down the other, aren't they totally different values? Have I convinced you that there aren't any derivatives at corners? And because of that, you do little circles. So that's how you deal with shapes that have straight lines in them. Use the corners to break the shape into regions. For each region, there'll be a straight line, right? So some of them are positive numbers. Some of the straight lines are horizontal, so negative. Some of them are pointing down, right? And you're finished. Are we good with that shape? Let's show you a curve again with a problem. Can you pretend that's half a circle? Because it's meant to be. And that's our function. And I am going to try and look at what its derivative function would look like. And we start off with the top of the hill. Would you agree that's 0? And so if I use that to, well, it's going to be on the y-axis, but I can still do it, right? It's going to look like that. We're going to have a guy there. Would you agree at x equals 0, the slope of the tangent line is also 0. Now, we don't have too many regions here. We only have 2. If you pick any point on this circle, would you agree that it's got a positive tangent line? Positive. And would you agree on this side here, they're all negative, right? And you might quite naturally think, oh, well, do you draw like a little straight line through them? You know, something like that, maybe. I mean, that's all the information you've got. There is another piece of information which is not obvious, but it is here. If I continue to circle, would you agree that at this point here, and same thing over here, wouldn't the tangent line be a vertical line? Right, straight up and down. What's the slope of a vertical line? What number, if it is a number, is the slope of a vertical line?
Isn't it undefined?
Right, and in the context of this, couldn't we also say it's infinitely large? Right, a vertical line has an infinite slope, right? You go infinitely upwards. Now, that means that for anything that's got a vertical touch to it, there is a vertical tangent line going on. So this shape actually looks like that. Would you agree the closer you get to the end, isn't the tangent line getting steeper and steeper and steeper, right? Getting more and more and more negative. And on this side, as you get closer to this side, isn't the tangent line getting bigger and bigger and bigger and bigger? And that's being reflected in these. Sneaky? That's what circles do. So if you see a thing that looks like a circle, you're probably going to end up with a guy that looks like that. Let's see, we covered all the possibilities. Yes, we have, I think. Yeah. Oh, I've just found one. Yes.
For these types of problems, will
Mhm.
they always be read from left to right? Or, you know what I mean? Because,
Well, I do them from left to right because that's the
Okay.
way. I can do them from right to left. I'll still go to get the same picture.
well, I mean, for the other graph that you have, where you have 5 regions, like if you were reading it differently, wouldn't it be flipped? Like
No,
for number
well,
1, like you see how like number 1 is positive, but if you're reading it from the other direction, then it would
Oh,
be
well,
negative.
this is always positive. We always read in that direction when you're indicating slope. So a slope that goes this way is considered positive, and a slope that goes that way is considered negative. So yes, we always do it from left to right. There isn't a choice. We good? Right, I just saw one more situation which can happen. It's not really a new situation. It's just putting two situations together. So imagine that we had a curve, and then at this point here, it decided to then become straight, right? That's a pretty weird shape, right? So what we have to figure out here is how to use the techniques that we've talked about, but blend them. See, on this side here, won't we use the, find out where it's 0, positive, and negative? And on this side here, won't we use the corners technique, right? So we're going to merge those two together and create a sketch of what the derivative function would look like. Okay, so I'm going to basically ignore that shape, pretend it's not there for a minute. Now, if you look at this shape, would you agree that there's only one place where there's a horizontal tangent line? And that means I will drop my little dotted line. These are little invisible lines that disappear after you've got the picture, and make a 0 happen there. So far, so good. Now I'm going to pretend that the curve's missing. When you do straight lines, aren't you interested in where the corners are? Would you agree? And so I'm going to take the corners now and drop them down. Now what that has done is it's broken this shape into region 1, region 2, region 3, and finally region 4. And for each one of those regions, depending if it's a curve or a straight line, we're going to, figure out what to do. Let's just do the pluses and minuses right now. In region 1, if you choose any point on this curve, will the slope be positive or negative? Region 1.
Negative.
Okay, so I'll just shade that. In region 2, what are you going to get?
Positive.
Okay, great. Now, since we now are cutting over to line 3, or region 3, which is a line, when you do lines, isn't the answer positive, 0, or negative? What are you going to get in line region 3?
0.
Positive,
0.
0. Oh, I just lost the mouse there. Right. I'm sorry I got distracted. I don't know. Did I get an answer and I missed it?
0.
0. We got it. Thank you. Can I just put a little guy here? Because I know it's 0. Right. Now, what about region 4? Would you agree it's a straight line, so it's the same number all the time? Positive, 0, or negative? What would that number be in region 4?
Negative.
And in region 4, I'll do a little negative line down here somewhere, right? Now we've got a curve going this way, meeting up with a horizontal line, meeting up with that. So I'm going to put a little circle here and circle here. That's good. Now for this shape here, couldn't we basically go like that? Oh, well, that just means they never meet. Are you comfortable about that combination and what it looked like?
Wait, for number 2 and number 1 are shaded. How
Yes.
come number 4 isn't shaded?
Well, I could shade it and then put a line through it after I shaded it. It's up to you if you feel you do what you feel you need to do. If it helps you see the picture by shading and then going back and adding the lines, that works for me just as well. Are we comfortable with that process? Because that's pretty much the end of these shapes.
I have a question.
Yes.
Is the slope of the region 4 line, is that a y in the derivative line?
Right. I'm not sure what you mean by y in the derivative line.
I will say like,
Yeah, that is like y equals 2 or minus 2, I should say in this case.
and so that would be the slope on
Yes.
the okay, gotcha.
So if that was a -3 slope, this would be at the height of -3, right? If this was a Well, that isn't. But if there was a plus slopey 5, you'd have a horizontal line here at a height of 5 to represent that. In this case, I'm not making any particular judgment call and saying, look, it's negative, so I pick something down there. Right. So I'm going to nip over and show you what the homework questions look like, because you know they have their own unique way of sometimes writing things down. Although I've done almost every one of these questions on paper, that's not how it works in WebAssign. What they do, hopefully, are you looking at it right now? Right. This is not going to work really well because I'm going to have to shrink it to the point where you probably can't see it. In this question, match the graph of each of the functions a to d with the graph of its derivative, right? So here is a. One of these 4 pictures ends up being a, okay? And if you take that curve and you do all the stuff, and then you got the answer, you will see a picture that looks very like one of these. It's a bit hard for people to tell just by looking, but I can tell 1, 2, 3, or 4. Which one do you think it would be for this blue curve A? What would its
4.
derivative curve look like?
4.
1, 2, 3, or 4?
4.
Agreed, it would be 4. But some of you are going to have to draw it and say, oh, that's 4, right? And that's fine. If I was going to do, yeah, here we go. B. Do you see B is made up of zigzag straight lines? It should be pretty obvious which one of those 4 came from a zigzag straight line graph. Right? I see lots of nods. Anybody want to tell me the 1, 2, 3, or 4 now?
2.
2, good. So you're nodding for the right reason, right? So do you see you don't write in WebAssign? Don't you write in scratch paper, then you pick the answer? Or sometimes you get good, can't you just visualize it in your brain? You know, oh, I kind of know what that's going to look like and do it that way. Here is a slightly different take on this. I don't like it when they put both pictures together. For some reason, my brain doesn't like it. I like them to be separate, one above the other, right? That's just me. If you took this curve and you then, and it's the blue guy, and you did the derivative on the same diagram, one of these pictures would be the derivative of this blue one. So do you see how they phrased that one? Anybody got a choice? Which one it is?
First one.
So you're going for this one here, is that right?
Yeah.
God, that F dash is so hard to see. The F dash is red. Let's see if you're right. You're going to go -0, positive. I like it. That's good. There's another one. Oh, remember the half circle that I just did? And can you see it's this picture here? You can't see it's this picture
No, it's
here?
the first one.
Oh, have I got it the wrong way around? You're right. It's the first one. I didn't even see that. That better be my answer the first time. Is that the answer I did when I did it? Yes, I think it was. So I'm good. Oh, haven't we done one almost like that a minute ago? Right. Figure out which one it is later. Here's one with some slopes. Figure it out. And then we move on to a totally different track. And that is the shortcut method. I probably get away with one more. I like it. The bigger it is, the better it is for my brain. My eyesight's not great. There we go. If I asked you to find the derivative function, wouldn't you just use the shortcut, right? So multiply by the power and reduce the power by 1. So in this case, I believe the answer would be 9t add 5. Agreed? Isn't the shortcut method so much easier than doing it the hard way, right? Now, state the domain of this function and enter it using interval notation. Would you agree that this function, the original function, you can use any value of t you like, all real numbers, but you're not allowed to type in all real numbers. I hope you can put a bracket and then a negative, and then you go hunting for infinity. Where will infinity be? Okay, tell me where infinity is hiding.
It's in symbols.
There we go. Oh, I skipped it. There. Negative infinity, comma, plus infinity with the brackets. That's what interval notation looks like. Okay. Would you agree that the derivative function has the exact same domain as the original? Would you agree that you can evaluate that for any value of t you like? And so that is your answer. It's not true that the domain of the original and the domain of the derivative are always going to be the same thing. But a lot of the time it will be, right? There will be exceptions. Sometimes the exceptions are just at the ends.
Is that because of something like that the piecewise functions that we saw?
Yeah, because sometimes the derivative of the original is okay, but the piecewise, the domain of the original is okay, but the derivative is piecewise and broke. And so there are going to be some problems. Or, remember the half circle one? The endpoints would be no good because they'd be vertical. So the endpoints, so instead of 1 to 1, square brackets mean you can use it, it would be curved brackets minus 1 to 1. So that could happen. Polynomial, pretty much the same question. Polynomial, same question. We haven't done this guy. So, have I got time? I do, great. So I haven't finished all possible shortcuts. We did a lot yesterday, did we? If I remember right, didn't we do things like x cubed and square root of x's? I think we did 1 over x squared or something and that, right? You can do it for functions that are even uglier than 1 over the square root of x. Okay. Now, for this function, I'm going to use the power rule. And this is where it's going to get messy. What fractional power is 1 over the square root of 4 plus x?
1/2.
Is it just 1/2? Because it is, but is there not something else as well?
Oh, wait a minute, yeah.
Because it's on the bottom,
Negative.
negative 1/2. Now, if the function had been just the square root of 4 of plus x, which I wish it would have been because that's easier to do, would you agree in this case, we could call it 4 plus x to the half, right? That would be, but can you see why this is negative 1/2? So far, so good. Now, isn't the power rule, you multiply by the power, no matter how ugly it is, and then you reduce the power by 1. So I'm going to multiply by the power and reduce the power by 1. And this shortcut that I'm just doing only works if this x is just an x, right? So 2 plus x and 2 plus 5x, it works totally fine. 2 plus x and 5 plus x, it works totally fine. But if it's 4 plus 2x or 4 minus 2x, you're going to have to do it the long way, right? The shortcut doesn't work. So you might get a question where you won't be able to do the shortcut. Now, we talked about style points yesterday. And one of the key rules of style points is, shouldn't you look like the original? So I'm going to call this negative 1 over 2 times 4 plus x to the 3/2. Are you with me? And then I'm going to do one more step. 3/2 is the same thing as the square root of 4 plus x cubed. Are you happy about that really ugly question? Turn it into a negative fractional power, use the power rule, and then a couple of lines of algebra, make it look like the original. Now, there's the domain of the original function, and it's going to be the domain of the derivative function. Now, if you, I'll take this over here for a minute. If you want to find the domain of this function, you're looking for usable values of x. Don't you need the inside square root to be positive? You can't get square roots in negative numbers. So you have to solve positive, which means x has to be greater than or equal to -4. But I am only going to use that. Why have I taken out x equals -4 as a usable value?
Because 0 doesn't work.
Correct. 1 over 0 is bad news, right? It doesn't work. So we are going to do is the domain, don't use -4, but anything bigger is fine. Would you agree that this guy has the same restrictions? So although the two are not always the same, a lot of the time they will be, right? Are we cool with that question now that we've kind of sussed it out? Right, let's go back and show you some more of the homework questions and talk through them. In this question, question 11, can't you just use the power rule? Now, it asks you here to check your answers, right? Now, if I do the derivative of this, are we happy with 4x cubed? Can I do cubed that way? All good. Are you happy that the derivative is that guy? Right. Now, in this case, we're being asked to use a graphing calculator recommended. I would say Desmos is recommended. So I'm going to do this on Desmos. So I'm going to have to make this guy go away. And I'm going to have to find Desmos. Go away, Desmos. And all I'm going to do is put in the first function and put in the second one. Maybe adjust the window a little bit, you know, because sometimes the windows aren't quite what we need. And I should be able to sketch this. Okay, I think I'm set up. No idea what you're saying right now, but you should be looking at Desmos. Are you looking at Desmos, guys? So the original function, right? The original was y equals 4x cubed plus, no, it wasn't, x to the 4. Plus 5x. Okay, looks a bit like that. I want to change the color on that. There we go. I want to make it blue because I like blue. Plus that's what it looks like in whatever sign. And the derivative, which we found, was y equals 4x cubed. Plus 5. And if you keep your mouse over it and you make it the left one, you can then change the color to red. And then I'm going to play about with this a little bit. Well, I can't play about with it too much. It looks something like that. And it's not a great fit because would you agree my x-axis is quite spread out? If I shrunk that in a little bit, it would look nicer. But that guy looks like, and my guy looks like the third picture. So that's one I would pick. It kinda lost it. Oops. Where are you? Yeah, it kind of looks like this. I'm saying that. Can you actually see the one I'm pointing at? No, you can. Oh, good. I never know this. Which ones? Okay. If I gave you this function and I said, looking at this graph, state the numbers, state the x coordinates where it would not be differentiable. Where on that graph do you think you're going to have a problem getting a derivative?
I can't see anything. If
Oh,
you're
I thought you were nodding and said, yeah, you could see it. And you weren't telling me the truth. You were telling me pork pies. Are you looking at it now? Okay. So make it a little bit bigger. That always helps me. Stop doing that. There we go. Make it a touch bigger. Why does it do that? Just because it makes things bigger. There. Give me the x coordinate of any point on that graph that you're going to have a problem finding the tangent line, because that's what they mean when they say it's not differentiable. Come on, give me some.
-4.
I agree. Would you agree that there's a corner? Corners are bad news. So there's my first answer. Come on. There's another blatantly obvious place where you're going to have a problem getting a derivative.
0.
Zero. And there is one hidden one that you're going to have a problem.
2.
Yes. What's wrong with 2?
The line is pretty much vertical.
Yeah, I think they're trying to make it vertical. And isn't vertical bad news for a derivative? Because it doesn't that mean the answer's infinite undefined? Right, here's another one. Give me, let's see. I can only see 2 places where there's a problem. Give me the x coordinates of places where you couldn't find a tangent line.
2.
Right, agreed? Corner, 2. Where's the other one?
-1.
-1. Now you might say, and I can understand why you might say that, but yeah, I could imagine what the tangent line would look like. Would you agree? But isn't the function not defined there? It's defined in the wrong place. That breaks it, right? You might be able to say, well, I know what the derivative should be, but that's not the same as what it would be equal to, because for a derivative to exist, doesn't the function have to be there, right? It has to be a dot there, not a hole. And that kills it. I think I can only see 2 problems. Anybody want to tell me the x coordinates of these problems?
1 and
1
5.
and 5.
You got both, nailed it. Would you agree vertical asymptotes are bad news for tangent lines? And would you agree that I think it's trying to be vertical at 5? I don't think you should write 4.9. I think it's just bad at drawing where it was. I think it should be 5. Now, it says here, use the definition of derivatives to find that guy. Well, use the shortcut. Now, if you differentiate this guy, you get 8x plus 3. You agree? Now, I don't know if you can see it because it's very tiny. Do you see there's a guy next to it called f double dashed? It's called the second derivative. What on earth do you think they want you to do?
Derive the derivative.
And the answer is A. And if they wanted to, couldn't you do a 3rd, 4th, and 53rd derivative? But in this case, it'd probably be 0, right? So once you've figured out that finding a derivative is a process, right? It's a thing you can do to a function. Can't you do it to the answer and get the second derivative? And do it to that answer and get the 3rd derivative? They actually do have meanings. They actually, you know, like the first derivative tells you the slope of the tangent line. Right? Second and third and various other derivatives like that don't tell you anything directly about the tangent line, but they do tell you about the movement of an object. So if you make the x-axis time and the y-axis position, then the first derivative tells you velocity. Remember the rock in Mars, the velocity story, right? First derivatives tell you velocity. What do you think second derivative tells you about an object?
Acceleration.
Yeah, it's the rate of change of velocity with time. And the third derivative and the fourth derivative, for some people who do further up the food chain, actually have names. I believe the third derivative is called, and this is being told to me by engineers and backed up by others, it's called jerk, J-E-R-K. So evidently, I know that word has other connotations, but evidently that's what it was called, right? And fine, you know. For me, I don't really care too much what engineers do with the math. Actually, that kind of bores me. What I find exciting is just math for math's sake. I just like math puzzles, right? But engineers say, oh, I don't want to know that. Oh, It helps me get acceleration. Oh, okay, I'm interested now, right? Or it helps me to tell the rate of change of voltage in a capacitor. Oh, I'm cool. I like that, right? Or whatever. And that's the part that excites engineers, right? That they like, what can I do with it? Whereas I just think it's kind of cool that you can do stuff. But right, would you agree first and second derivative of this kind of makes sense? And they go on and they say check by calculus. I'm never sure if you draw the graphs of these that it really helps you to know if you've done it right. Would you agree that the derivative graph and then the second derivative graph aren't that easy to say, oh yeah, that's obvious that I did it right? But I mean, if you want to, you can. Oh, there's a cool one. The first derivative is going to be 4x take away 3x squared. And then the second derivative is the derivative of the guy I just wrote. So that's 4 take away 6x. And the third derivative is -6. And have you noticed I get this funny little bracket thing? Once you get beyond the third derivative, Roman numerals aren't very helpful. Can you imagine somebody using, you know, XVII, right, Roman numerals, to do the 23rd derivative? Right, people would say, what's XXIV? I don't know what XXIV is. I don't know that. So don't they just put a little bracket and call it 24? Right. And so if you're wondering what that is, what is the fourth derivative then? What do you get if you differentiate -6?
0.
Make that 0. In fact, won't the 5th, 6th, and the 43rd derivatives all be 0? Right, in this case, you know, once you hit 0, nothing happens. And then they give you a really messy looking picture, but good luck figuring it out. And do you know what I would do? Do it in Desmos and have a look at it, right? And then one of these pictures, and there's 4 of them, will be the guy you want. Okay, we did this yesterday. What fractional power will you call that guy?
1/3.
Right, and can't you use the power rule shortcut? And oh, guess what? They're back to A's, just for fun and giggles. So don't write your answer as 2/3, you know, cube root of t, call it 2/3 cube root of a, right, if that's what you get. Would you agree this guy is good to go with power rule? Right. Just remember that if they stick an A in here, make your answer have A's. If they stick a, you know, an A here, make your answer in A's. Now, if it said f dashed of t, wouldn't you do the same expression but t's? So when I say something's cosmetic, I'm just looking and saying, isn't it really the same answer if you put an A, an X, or a T, right? Algebraic, it's the same thing, right? The A, the X, or the T is just the lettering that they want to use for whatever answer. And I call that perfect timing. We have finished. Your online test 3 will be available in about 9 minutes or earlier. You don't need to do it. In fact, don't until Sunday midnight or whenever you're ready on Sunday. And it's containing a